Okay, hi everyone. Let's get started again. Okay, so first of all, for a couple of announcements. First of all, thanks to everyone who filled in our mid-quarter survey. We actually got great participation in that. Here are my two little Pac-Man figures. So the Pac-Man figures means that almost everyone thinks the lecture's at the right pace, and those that don't are pretty much evenly divided. If we go for how challenging was assignment 3, slightly more people thought it was too easy than too hard. So I guess we're setting about rectifying that with assignments 4 and 5. So there are a whole bunch of other questions, and we've been trying to absorb all the feedback. I mean, one of the questions was what people wanted most from the remaining lectures. I guess the good news here is really we were very good at predicting what people wanted. That or else everybody just looked ahead in their syllabus and wrote down what it said was ahead in the syllabus. But I guess the most popular 4 answers to topics that they wanted in the remaining lectures were transformers and BERT, both of which are going to be covered this week, question answering, which we talked about last week, and then text generalization and summarization, and you guys get Abby back next week to talk about that. There are also, a lot of people also answered this question a different way as to what kind of style of stuff. Some people emphasized new research and the latest updates from the field. I guess we'll get some of that today as well. Some people were more interested in successful applications in industry. We'll try and do a bit of that. Cool new neural architectures. The bottom answer wasn't the most popular one, I'll admit, but at least a few people wish that we were teaching more linguistic stuff. I mean, that is something that I actually feel a bit awkward about, the way things have emerged with CS224N, with this deep learning. I mean, the truth of the matter is it sort of seems like in the early part of the course, there's so much to cover with neural networks, backpropagation, different neural net architectures and so on, that the reality is that we teach rather less linguistic stuff than we used to in the class. I mean, for the last 4 weeks of the class, we really do try and cover some more linguistic stuff topics, so look forward to that. Announcements. Okay, so we've made a couple of deadline changes. Firstly, a number of people have mentioned that they think assignment 5 is a bit tough, and so we're giving people 1 extra day to do assignment 5. I realize in one sense that 1 extra day is not a ton, but you know, there's sort of this complex balance here, because on the other hand, we don't really want to undermine time that people have available for final projects. And if you're one of the people who hasn't yet started assignment 5, we do really encourage you to get underway on it. Yeah, in the reverse direction, we decided that the project milestone was really too late if we were going to be able to give you feedback on it that you could usefully make use of. So we're moving the project milestone date 2 days earlier. And so we've also gotten everyone's project proposals, and our hope is to get them back to everybody on Friday. Yeah, so a lot of things moving. And finally, on other announcements, I guess on this Thursday is our first invited speaker. And so if you're in-person student, you're meant to be here. And if you're not able to be here, you should know about our reaction paragraph policy. And I actually stuck up on the Piazza pin post about reaction pieces in attendance, an example of a reaction piece from a past class to make it a little bit more concrete what's expected there. But you know, the idea is what we're hoping for is something that isn't a ton of work. You can just write 100, 150 words, a few sentences, but wanting you to pick out a specific thing that was interesting and write a couple of sentences about what it was and what your thoughts are about it, i.e. not just some very generic statement of this was a lecture about transformers, he talked about transformers and it was interesting. That is not what we want for the reaction piece. Okay, so here's the plan for today. So for today's, what I want to talk about is the exciting recent work about contextual word representations. I mean, I was thinking over what I was going to say. I was wanting to say, oh, this is the most exciting thing in deep learning for NLP in the last 5 years. But in some sense, that's completely wrong, because really, this is the most exciting thing in deep learning that happened in 2018. I mean, I guess things move very quickly in deep learning at the moment, and it's sort of, I don't think it's really fair to say that, you know, it's got 5 years of life. But it's a very exciting thing that happened last year, and we'll talk about that. Okay, so we'll talk about early stuff, ELMo, ULMFiT, transformer architectures briefly, and then go on to talk about the BERT model that's been quite prominent lately. So let's just go backwards a bit first to think about where we've been and where we are now and why we might want something more. So up until now, we've sort of just had one representation for words, which is what we learned at the beginning of class. There was a word, you trained a word vector for it, and that's what you used in your model. And you could do that with algorithms like word-to-vec-glove or fast text that I mentioned last week. So on this sort of progression of ideas in deep learning, when deep learning for NLP, or in general just the resurgence of neural networks for NLP came about sort of at the beginning of this decade, these pre-trained word vectors, so pre-trained unsupervised over a large amount of text, they were completely seen as the secret sauce, and they were the thing that transformed neural networks from NLP to something that didn't really work to something that worked great. So this is actually an old slide of mine. So this is a slide I guess I first made for a 2012 ACL tutorial, and then sort of used in lectures sort of in 2013, 2014. And so this was sort of the picture in those years. So this is looking at two tasks, part of speech tagging and named entity recognition, which I'll use quite a bit today. And you know, the top line was showing a state-of-the-art, which was a traditional categorical feature-based classifier of the kind that dominated NLP in the 2000s decade in their performance. And what then the next line showed is that if you took the same data set and you trained a supervised neural network on it and said, how good is your performance, the story was it wasn't great. Part of speech tagging has very high numbers always for various reasons. So perhaps the more indicative one to look at is these named entity recognition numbers. So, you know, this was sort of neural net suck, right? The reason why last decade everybody used categorical feature-based, you know, CRF, SVM kind of classifiers. Well, look, it works 8% better than a neural network. Why wouldn't anybody? But then what had happened was people had come up with this idea that we could do unsupervised pre-training of word representations to come up with word vectors for words. And you know, in those days, this was very hard to do. Both because of the kind of algorithms and the kind of machines that were available, right? So Colbert and West in 2011 spent 7 weeks training their unsupervised word representations, and at the end of the day, they're only 100-dimensional word representations. But this was the miracle breakthrough, right? You put in this miracle breakthrough of unsupervised word representations, and now the neural net is getting to 88.87, so it's almost as good as the feature-based classifier. And then, like any good engineers, they did some hacking with some extra features, gazettes and stuff like that, and they got a system that was then slightly better than the feature-based system. Okay, so that was sort of our picture, that having these pre-trained in unsupervised manner word representations, that was sort of the big breakthrough and the secret sauce that gave all the oomph that made neural networks competitive. But sort of a funny thing happened, which was after people had sort of had some of these initial breakthroughs, which were all about unsupervised methods for pre-training. It was the same in vision. This was the era in vision where you were building restricted Boltzmann machines and doing complicated unsupervised pre-training techniques on them as well. Somehow, after people had kind of discovered that and started to get good on it, people sort of started to discover, well, actually, we have some new technologies for nonlinearities, regularization, and things like that. And if we keep using those same technologies, we can just go back to good old supervised learning, and shockingly, it works way better now inside neural networks. And so if you sort of go ahead to what I'll call a sort of 2014 to 2018 picture, the picture is actually very different. So the picture is, the results I'm actually going to show, this is from the Chen and Manning neural dependency parser that we talked about weeks ago. The picture there was, despite the fact that this dependency parser is being trained on a pretty small corpus, 1 million words of supervised data, you can just initialize it with random word vectors and train a dependency parser. And to a first approximation, it just works fine. You get sort of a 90% accuracy English dependency parser. Now, it is the case that instead you could use pre-trained word embeddings, and you do a bit better. You do about 1% better. And so this was sort of the new world order, which was, these pre-trained unsupervised word embeddings are useful because you can train them from a lot more data and they can know about a much larger vocabulary. That means they're useful. They help with rare words and things like that, and they give you a percent. But they're definitely no longer the sort of night and day thing to make neural networks work that we used to believe. I'm just going to deviate here from the main narrative to just sort of say one more tip for dealing with unknown words with word vectors, just in case it's useful for some people building question answering systems. Right, so for sort of word vectors and unknown words, the commonest thing historically is you've got your supervised training data, you define a vocab, which might be words that occur 5 times or more in your supervised training data, and you treat everything else as an UNC, and so you also train one vector for UNC. But that has some problems, which you have no way to distinguish different UNC words either for identity or meaning, and that tends to be problematic for question answering systems. And so one way to fix that is what we talked about last week. You could say, well, words made out of characters. I can use character representations to learn word vectors for other words. And you can certainly do that. You might want to try that. That adds some complexity. But especially for things like question answering systems, there are a couple of other things that you can do that work considerably better, and they've been explored in this paper by Dinger et al. From 2017. The first one is to say, well, when you at test time encounter new words, probably your unsupervised pre-trained word embeddings have a much bigger vocabulary than your actual system does. So anytime you come across a word that isn't in your vocab but is in the pre-trained word embeddings, just get the word vector of that word and start using it. That'll be a much more useful thing to use. And then there's a second possible tip that if you see something that's still an unknown word, rather than treating it as UNC, you just assign it on the spot a random word vector. And so this has the effect that each word does get a unique identity, which means if you see the same word in the question and a potential answer, they will match together beautifully in an accurate way, which you're not getting with just UNC matching. And those can be kind of useful ideas to try. Okay, end digression. Okay, so up until now, we just sort of had this representation of words. We ran word to vec and we got a word vector for each word. That was useful. It's worked pretty well, but it had some big problems. So what were the big problems of doing that? Big problems of having a word vector each word? Yes?
A lot of words have like one spelling but a whole bunch of meanings.
Right, so a word can have, so typically you have one string of letters which has a whole bunch of meanings. So words have a ton of senses. And yeah, so that's the biggest and most obvious problem, that we're collapsing together all the meanings of a word. So we talked about a bit, well, one solution to that was you could distinguish word senses and to have different word vectors for them. And I then said something about, so you could think of this word vector as a sort of a mixture of them and maybe your model could separate it. But it seems like we might want to take that more seriously. And one way that we could take that more seriously is we could start to say, well, really, you know, traditional lists of word senses are themselves a crude approximation. What we actually want to know is the sense of a word inside a particular context of use. And sort of what I mean by that is, you know, we distinguish different senses of a word, right? So for the word star, there's the astronomical sense and there's the Hollywood sense, and they're clearly different. But, you know, if we then go to this, what I'm calling the Hollywood sense, I could then say, well, wait a minute, there are movie stars and there are rock stars and there are R&B stars and there are country stars. Now, all of those different senses, in certain contexts, though, one or other of them would be evoked. And so, you know, it's very hard if you're trying to actually enumerate senses of a word as to which ones count as different or the same. So really, you sort of want to know what a word means in a context. There's a second limitation of these word vectors, which is we haven't really talked about and is less obvious, but it's also something that we might want to fix, and at least one of the models we discussed today takes some aim at that. And that is, we've just sort of had one vector for a word, but there are sort of different dimensions of a word. So words can have different meanings, or sort of real semantics, or words can have different syntactic behavior, like different parts of speech or grammatical behavior. So in some sense, arrive and arrival, their semantics are almost the same, but they're different parts of speech. One's a verb and one's a noun, so they can kind of appear in quite different places, and you know, you'd want to do different things with them in a dependency parser. And there are even other dimensions. So words also have register and connotation differences. So you can probably think of lots of different words for a bathroom, and a lot of those words all mean semantically the same, but have rather different registers and connotations as to when they're appropriate to use. And so we might want to distinguish words on that basis as well. And so these are the kind of solution things we want to solve with our new contextual word embeddings. So I've said up until now, you know, we just had these word vectors that we use. Words just had one vector. But if you actually think about it, you know, maybe that's wrong. I mean, maybe we never had a problem, or at any rate, we'd solved it 6 classes ago. Because if you remember back to when we started talking about neural language models, well, what did a neural language model do? At the bottom, you fed into it the word vectors, but then you ran across that one or more recurrent layers, something like an LSTM layer, and it was calculating these representations that sit above each word. And, you know, the role of those hidden states is a bit ambivalent. They're used for prediction, they're used for next hidden state and output states and so on. But in many ways you can think, these representations are actually representations of a word in context. And if you think about what happened with the question answering systems, that's exactly how they were used, right? We ran LSTMs backwards and forwards over a question and a passage, and then we say, okay, those are a good representation of a word's meaning and context. Let's start matching them with attention functions, etc. So it sort of seemed like we'd already invented a way to have context-specific representations of words. And effectively, you know, the rest of the content of this lecture is sort of basically no more complex than that. That it took a while, but sort of people woke up and started to notice, really when you're running any language model, you generate a context-specific representation of words. Maybe if we just took those context-specific representation of words, they'd be useful for doing other things with them. And that's sort of, you know, there are a few more details, but that's really the summary of the entire of this lecture. So one of the first things to do that was a paper that Matt Peters wrote in 2017, the year before last. And this was sort of a predecessor to the sort of modern versions of these context-sensitive word embeddings. So together with co-authors, he came up with a paper called Tag LM, but it essentially already had all the main ideas. So what was wanted was, okay, we want to do better at tasks such as named entity recognition, and what we'd like to do is know about the meaning of a word in context. But, you know, standardly, if we're doing named entity recognition, we just train it on 500,000 words of supervised data, and that's not much of a source of information to be learning about the meaning of words in context. So why don't we adopt a semi-supervised approach? And so that's what we do. So we start off with a ton of unlabeled data, and from that unlabeled data, we can train a conventional word embedding model like word2vec, but we can also at the same time train a neural language model, so something like by LSTM language model. Okay, so then for step 2, when we're using our supervised data, actually I guess that's step 3. Okay, so for then when we want to learn our supervised part of speech tagger up the top, what we're going to do is say, well, for the input words, New York is located, we can not only use the word embedding, which is context independent, but we can use our trained recurrent language model and also run it over this input, and then we'll generate hidden states in our by LSTM language model, and we can also feed those in as features into our sequence tagging model, and those features will let it work better. Here's a second picture that runs this through in much greater detail. So we're assuming that we have trained by LSTM language model on a lot of unsupervised data. Then what we want to do is we want to do named entity recognition for New York is located. So the first thing we do is say, let's just run New York is located through our separately trained neural language model. So we run it through a forward language model, we run it through a backward language model, we get from that a hidden state representation for each word. We concatenate the forward and backward ones, and that's going to give us a concatenated language model embedding, which we will use as features in our named entity recognizer. So then for the named entity recognizer itself that we're going to train supervised, well, we have the same sentence, so we can both look up a word2vec style token embedding for it. We can use what we learned about with character level CNNs and RNNs, and we can build a character level representation for it, which we also concatenate to have two representations. So we feed these representations into a BioSTM layer. But then when we get the output of this BioSTM layer, as well as its normal output, we can concatenate with each output what we get from our neural language model. So each of these things becomes a pair of states, one that's fed up from the first BioSTM layer, and then it's concatenated with something from the neural language model. And so that concatenated representation is then fed into a second layer of BioSTM, and then from the output of that, we do the usual kind of softmax classification, where we're then giving tags like beginning of location, end of location, to say New York is a location, and then will get an other tag to say it's not a location. Does that make sense? Yeah, so the central thing is sort of having seen that these sort of representations that we get from BioSTMs are useful, we're just going to feed them into supervised models as we train them. And the idea is that will give us better features of words, some kind of representation of their meaning and context, which will allow us to learn better named entity recognizers or whatever it is. Maybe I should have put this slide earlier, but this slide was meant to remind you what a named entity recognizer is. I hope you remember that. Something where we're going to find and label entities for things like person, location, date, organization. So anyway, doing this worked. So here's a little bit of a history. So the most famous named entity recognition data set is this Connell 2003 data set, which actually exists in multiple languages. But whenever people say Connell 2003 and don't mention a language, they mean the English version of it. That's the way the world works. Okay, so on this data set, yeah, so it's sort of been around for whatever, 15 years roughly now. So it was originally a competition, right? So this in 2003 was the original bake-off. My group actually took part in it. I think we got third or fourth place or something, and our F1 score was 86. The people who won were from IBM Research Labs, and they got 88, almost 89. But a difference between these two things is our system was a single clean machine learning model, categorical, whereas the IBM one was not only an ensemble of 4 different machine learning models plus gazetteers. It also fed in the output of 2 other old NER systems that IBM people had trained years ago on different data. So I guess it worked for them, but it was a fairly complex system. Here's another system from Stanford. So this was our classic Stanford NER system that is widely used. So this was then using a conditional random field model, which generally dominated sort of the second half of the 2000s and the first half of the 2010s for doing NER, and it was sort of, a bit but not hugely better than the 2003 system. This system here was sort of the best ever built categorical CRF system, but rather than only using the training data to build the model, as this system did, it threw in Wikipedia and other stuff to make it work better, and that got you to about 90.8 F1. So essentially, once sort of BioSTM style models started to be known and used in NLP, that was when people were able to build training just on the training data systems that worked a lot better, because essentially you're going from the same data from this system to that system, so you're getting about 4% gain on it because wasn't making use of Wikipedia and things like that. And so this Marr and Hovey system is pretty well known, getting about 91.21. Okay, but if we then go to this TAG-LM system that Matt Peters and co. have a system that was sort of similar to the Maher-Hovey system, but did a little bit worse. But their point is that this BioSDM, using the neural language model is just a useful oomph giver, which sort of takes the results up, not night and day, but slightly over 1%, and then gives them the best NER system that was then available. So that sort of proved these sort of contextual word representations really had some power and started to be useful. And then there's a white space at the top because we'll get back to more of this later. There are some details on their language model. Some of their details are that it's useful to have a bidirectional language model, not unidirectional. It's useful to have a big language model to get much in the way of gains. And you need to train this language model over much more data. It doesn't work if you're just sort of training it over your supervised training data. Another model that was around was Cove, but I think I'll skip that. Okay, so then the next year, Matt Peters and a different set of colleagues then came up with an improved system called ELMo. And effectively, this was the breakthrough system, that this was sort of just the system that everybody noticed and said, wow, these contextual word vectors are great. Everyone should be using them, not traditional old word vectors. Yes?
Simple question. When you mentioned the pre-trained system, what exactly is pre-trained on? What kind of objects are you trying to utilize? Is it kind of, it seems from your graph that the hidden layer you train kind of go back into the LCM that we use later on. But why is this called pre-trained? Is it like a...
It's pre-trained because this piece over here, a big neural language model, is trained first. And there's an important thing I forgot to say, so thank you for the question. The main reason why it's in some sense pre-trained is this was trained first. But the main reason why people think of this as pre-training is after you've trained this, it is frozen. So this is just something that you can run with parameters, which will give you a vector, which is your contextual word representation at each position. And then that's just going to be used in this system. So when you're training this system, there's no gradient flowing back into this neural language model that's changing and updating it. It's just fixed. And so that's sort of the sense when people are talking about pre-training, it's sort of normally a model that you trained somewhere else and that you're using to give features, but isn't part of the model that you're now training. Yeah?
You mentioned it is unsupervised. Is it just trained on the laws or reconstruction?
Well, I guess it's I wouldn't quite call it reconstruction. Yeah, it's unsupervised in the sense that this is a language model. You're training it to predict the next word. So here are words 1 to k. What is the k plus 1th word? Doing a cross entropy loss and repeat over for each position. Yeah, so I mean, having gone through tag, LM in some detail, I mean, in some sense the difference between tag LM and ELMo is kind of small. It's sort of in the details. I mean, to a first approximation, they're doing exactly the same again, but a little bit better. I sort of hope it made sense the last time. I mean, what are the things that are different? They do the bidirectional language model a bit differently. And actually one of their concerns was to try and come up with a compact language model that'd be easy for people to use in other tasks, even if they don't have the beefiest computer hardware in the world. And so they decided to dispense with having word representations altogether and just use character CNNs to build word representations, because that lessens the number of parameters you have to store, the big matrices you have to use. They expanded the hidden dimension to 4096, but then they project it down to 512 dimensions with a sort of feed-forward projection layer, and that's a fairly common technique to, again, reduce the parameterization of the model so that you have a lot of parameters going in the recurrent direction, but you need much smaller matrices for including the input at the next level. Between the layers, they now use a residual connection, and they do a bit of parameter tying. So it's sort of all in the little details there. But there's another interesting thing that they did, which was an important innovation of ELMo, so we should get this bit. So in TAG-LM, what was fed from the pre-trained LM into the main model was just the top level of the neural language model stack. And that was completely standard de rigueur in those days, that you might have had 3 layers of neural language model, but you regarded the top level as your sort of one that's really captured the meaning of the sentence, and the lower layers were processing that led up to it. And they had the idea that maybe it would be useful to actually use all layers of the BISD of the neural language model. So maybe not just the top layer, but all layers would be kind of useful. So there are these kind of complex equations, but essentially the point of it over here is we're going to, for a particular position, word 7 in the language model, we're going to take the hidden state at each level of our neural language model stack. We're going to learn a weight for that level. We're going to sort of sum them. So this is sort of a weighted average of the hidden layers at each position. And that will be used as our basic representation. And so they found that that gave quite a bit of extra usefulness and different tasks could prefer different layers. There's one other bit here, which is they learn a global scaling factor gamma for a particular task. And this allows them to control that for some tasks, the contextual word embeddings might be really useful, and for other tasks they might not be so useful. So you're just sort of learning a specific usefulness for the entire task. Okay, so that's their sort of new version of language model. But this is allowing this idea of, well, maybe there's sort of more syntactic meanings of a word and more semantic meanings of a word. Possibly those could be represented at different layers of your neural language model, and then for different tasks you can differentially weight them. So that's the basic model. So you run your BioSTM before to get representations of each word. And then their generic ELMo recipe was, well, with that frozen language model, you want to feed it into some supervised model depending on what the task was. And they sort of say in the paper, well, how you do this maybe depends on the task. You might want to kind of concatenate it to the intermediate layer, just as the TAG-LM did. That might be fine. But, you know, it might also be useful to make use of these ELMo representations when producing outputs. So if you're doing something like a generation system, or you might just sort of feed in the ELMo representation again before you sort of do the softmax to find the output. They sort of left it flexible as to how it was used. But the general picture, you know, was kind of like we saw before. Indeed, I'm reusing the same picture, that you've calculated an ELMo representation for each position as a weighted average, and then you're sort of concatenating that to the hidden state of your supervised system and generating your output. At any rate, one way or another, they were able to do this, and with the little improvements, that gave them about an extra 0.3% in named entity recognition. Now that sort of sounds like not very much, and you might conclude from this, why the excitement? And, you know, in some sense, That's right, because sort of to the extent that there was an interesting idea here, really they'd come up with it for the tag LM paper, which gave a much better gain. But you know, why everyone got really excited was that in the ELMo paper, they then showed this isn't something that you can do one-off to improve a named entity recognizer. You can take these ELMo representations and use them for pretty much any NLP task, and they can be very useful and give good gains. And so essentially why people got excited was because of the data that's in this table. So here we're taking a whole bunch of very different tasks. So there's squad question answering, there's natural language inference, there's semantic role labeling, there's co-reference, the named entity recognition, doing sentiment analysis, so a wide range of different NLP tasks, and that they have a previous state-of-the-art system. They produce their own baseline, which is, you know, commonly sort of similar to the previous state-of-the-art, but usually actually a bit worse than the current state-of-the-art because it's whatever simpler, cleaner system that they came up with. But then they could say in each case, oh, just take this system and add ELMo vectors into the hidden representations in the middle and have those help you predict. And in general, in all cases, that's giving you about a 3% or so gain absolute, which was then producing this huge performance increase, which in all cases was moving the performance well above the previous state-of-the-art system. So, you know, this sort of then made it seem like magic pixie dust, because, you know, in the stakes of NLP conference land, you know, a lot of people used to trying to come up with a paper for the next year that's 1% better on one task and writing it up, and that's their big breakthrough for the year to get their new paper out. And the idea that there's just, well, this way of creating context-sensitive word representations, and you just use them in any task, and they'll give you around 3% and take you past the state-of-the-art. This seemed like it was really great stuff. And so people got very excited about this, and it won the Best Paper Award at the NACL 2018 conference. And then, as I sort of vaguely mentioned, so the model that they actually used wasn't a deep stack. There were actually only 2 layers of bio-STMs. But they do show this interesting result that the lower level better captures low-level syntax, word properties, and is most useful for things like part-of-speech tagging, syntactic dependencies, NER, where the top layer of their language model is better for higher level semantics and is more useful for things like sentiment, semantic role labeling, and question answering. So that seemed interesting. That would actually be interesting to see how that panned out more if you had sort of more layers to play with. Okay, ELMo, done. So moving right ahead, here's something else that I just thought I should mention a little bit about. Another piece of work that came out around the same time, a few months later, maybe, or maybe not. Came out around the same time in 2018 was this work on universal language model fine-tuning for text classification, or ULMFiT by Howard and Ruder. And essentially this had the same general idea of saying, well, what we want to do is transfer learning where we could learn a big language model, and then for our target task, which might be named entity recognition, but here is text classification, we can transfer this language model information and help us to do better with the task. And so they proposed an architecture to do that. And so their architecture was, you have a big unsupervised corpus from which you train a neural language model. They used a deeper neural language model with 3 hidden layers. You then fine-tune your neural language model on the actual domain that you're interested in working in. So this was sort of an extra stage that they did. And then finally, you now introduce your classification objectives. So what they're going to be doing is making text classifiers. So we're now wanting to take this model and turn it from a language model into a text classifier. But there's something that they did differently, which is in some sense foreshadows the later work in transformers. So rather than just feeding features from this into a completely different network, they keep using the same network, but they introduce a different objective at the top. So one thing you could do with this network is use it to predict the next word as a language model. And so at this point, they freeze the parameters of that softmax at the top. That's why it's shown in black. But instead, they could stick on a different prediction unit where it's predicting stuff for a particular task. So it might be predicting positive or negative sentiment in a text classification task or something like that. So in their model, they're sort of reusing the same network, but sticking on the top of it a different layer to do their new classification task. They were also interested in something small, the sort of 1 GPU model of research. The paper has a lot of detail as sort of tricks and care and feeding of your neural models to maximize performance. If you're interested in that, you could sort of look up some of the details about that. But what they were able to show, again, was making use of this language model pre-training was a very effective way to improve performance, this time for text classification. So these are text classification data sets. IMDb is for sentiment. TREC is for topical text classification. And again, there are preceding systems that other people have developed, and they're showing that by making use of this language model pre-training, they're able to significantly improve on the state of the art. So these are error rates, so that low is good. They also showed another interesting result, which is kind of what you would expect or hope from doing this kind of transfer learning, that what they were able to show is if you can train this neural language model on a big amount of data, that means you'll then be able to do well on your supervised task, even when trained on pretty little data. So here, this is error rate, so low is good. And so and here's the number of training examples, which is being done on a log scale. And so the blue line is if you're just training a text classifier from scratch on supervised data. So you need a lot of data to start to do pretty well. But if you're making use of this transfer learning from a pre-trained language model, you can get to that you're sort of doing pretty well with way less training examples. Essentially, an order of magnitude less training examples will give you the same amount of performance. And the difference between these two lines corresponds to the extra phase that they had in the middle of theirs, which is whether you're doing this sort of extra fine-tuning on your target domain is part of your process, and they found that to be pretty helpful. Okay, so that is another precursor. And so one big part of what has happened since then is effectively people have said, this is a good idea. Maybe it'll become a really, really good idea if we just make things way bigger. So ULMFiT was something that you could train in 1 GPU day. Sounds appealing for CS224N final projects, remember that. But then the people at OpenAI decided, well, we could build a pre-trained language model and train it on a much larger amount of data, on a much larger amount of compute, and use about 240 GPU days, and that will get a lot better. And it did. And then the people at Google said, well, we could train a model in 256 TPU days, which means maybe about double the amount of computation. It's hard to figure out exactly. And that might be able to do exciting things. And that was the BERT model, and it did. And then if you're following along these things, just last week, the OpenAI people said, well, we can go much bigger again, and we can train a model for approximately 2,000 TPU version 3 days, and it will be able to do much bigger again, much better again. And so this is this GPT-2 language model, which OpenAI released last week. And there are actually very impressive results when they're showing that if you're sort of building a really, really huge language model over a very large amount of data, and then you say, language model, go off and generate some text on a particular topic, that it can actually just do a great job of producing text. So the way this was being done was a human is writing a couple of sentences. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. And so we're then using our neural language model and chugging through that, so that gives us context, and then say generate more text, and it starts to generate the scientist name, the population after their distinctive horn, Ovid's unicorn. These 4-horned silver-white unicorns were previously unknown to science. It produces remarkably good text, or at least in the hand-picked examples that they showed in the tech news, it produces extremely good text. So I think one should be a little bit cautious about that, and sort of some of its random outputs actually aren't nearly as good. But nevertheless, I think it is actually dramatic how good language models are becoming once you're training them on long contexts, as we can do with modern models, on vast amounts of data. So then the OpenAI people decided this language model was so good that they weren't going to release it to the world, which then got transformed into headlines of Elon Musk's OpenAI builds artificial intelligence so powerful it must be kept locked up for the good of humanity, with the suitable pictures that always turn up at these moments down the bottom of the screen. I guess that was it, leading even Elon Musk to be wanting to clarify and say that it's not actually really that he's directing what's happening at OpenAI anymore. Anyway, moving right along. So part of the story here is just a scaling thing, that these things have been getting bigger and bigger. But the other part of the story is that all three of these are then systems that use a transformer architecture. And transformer architectures have not only been very powerful, but technically have allowed scaling to much bigger sizes. So to understand some of the rest of these, we should learn more about transformers. And so I'm sort of going to do that. But I mean, in mix of orders, our invited speaker coming Thursday is one of the authors of the Transformer paper and is going to talk about transformers. So I think what I'm going to do is say a little bit about transformers quickly, but not really dwell on all the details, but hope that it's a bit of an introduction and you can find out more on Thursday about the details, and then talk some more about the BERT model before finishing. So the motivation for transformers is essentially we want things to go faster so we can build bigger models. And the problem, as we mentioned, for these LSTM or in general any of the recurrent models is the fact that they're recurrent. You have to generate sort of one hidden state at a time chugging through, and that means you just can't do the same kind of parallel computation that GPUs love that you can do in things like convolutional neural networks. But on the other hand, we discovered that even though these gated recurrent units like LSTMs and GRUs are great, that to get really great performance out of these recurrent models, we found that we wanted to we had a problem with these long sequence lengths, and we could improve things by adding attention mechanisms. And so that led to the idea of, well, since attention works so great, maybe we can just use attention and we can actually get rid of the recurrent part of the model altogether. And so that actually then leads to the idea of these transformer architectures, and the original paper on this is actually called Attention is All You Need, which reflects this idea of we're going to keep the attention part and we're going to get rid of the recurrent part, and we'll be able to build a great model. So in the initial work, what they're doing is machine translation, kind of like the neural machine translation with attention we described. But what they're wanting to do is build a complex encoder and a complex decoder that works non-recurrently and nevertheless is able to translate sentences well by making use of lots of attention distributions. And so I wanted to say a little bit more quickly about that, and hopefully we'll get more of this on Thursday. First, as a recommended resource, if you want to look at home and learn more about the transformer architecture, there's this really great bit of work by Sasha Rush called the Annotated Transformer that goes through the entire transformer paper, accompanied by PyTorch code in a Jupyter notebook. And so that can actually be a really useful thing. But I'll go through a little bit of the basics now of how we do things. So the basic idea is that they're going to use attention everywhere to calculate things. And we talked before about the different kinds of attention, of the sort of multiplicative bilinear attention and the little feed-forward network additive attention. They kind of go for the simplest kind of attention, where the attention is just dot products between two things. But they sort of do the more for various purposes, they do the more complicated version of dot product between two things, where they have when the things that they're looking up are assumed to be key value pairs, keys and values. And so you're calculating the similarity as a dot product between a query and the key. And then based on that, you're going to be using the vector for the corresponding value. So our equation here for what we're calculating is we're looking using the softmax over query key similarities, and using that to give the weightings as an attention-based weighting over the corresponding values. So that's their basic attention model. So that saying it that way adds a little bit of complexity, but sort of for the simplest part for their encoder, actually all of the query keys and values are exactly the same. They're the words that they're using as their source language thing. So it sort of adds some complexity that isn't really there. Okay, I'll skip that. So there are a couple of other things that they do. One thing that they note is that the values you get from QTK vary in variance as the dimension gets large, so that they sort of do some normalization by the size of the hidden state dimension, but I'll leave that out as well for details, right? So in the encoder, everything is just our word vectors. They're the queries, the keys, and the values. And we're going to use attention everywhere in the system. Oops. Okay, so the second new idea is, well, attention is great, but maybe it's bad if you only have one attention distribution, because you can only attend to things one way. Maybe for various uses, it'd be great if you could attend from one position to various things. So if you're thinking about syntax and what we did with dependency parsers, if you're a word, you might want to attend to your head word, but you might also want to attend to your dependent words. And if you happen to be a pronoun, you might want to attend to what the pronoun refers to. You might want to have lots of attention. So they introduced this idea of multi-head attention. And so what you're doing with multi-head attention is you have your hidden states in your system, and you map them via projection layers, which are just multiplications by different W matrices as linear projections into sort of different lower dimensional spaces. And then you use each of those to calculate dot product attention. And so you can attend to different things at the same time. And this multi-head attention was one of the very successful ideas of transformers that made them a more powerful architecture. Okay, so then for our complete transformer block, it's sort of then starting to build complex architectures like we sort of started seeing the other week. So starting from our word vectors, we're kind of going to do attention to multiple different things. And we're simultaneously going to have a residual connection that short circuits around them. We're then going to sort of sum the two of these, and then they're going to do a normalization at that point. I talked previously about batch normalization. They don't do batch normalization. They do another variant, which is layer normalization, which is a different way of doing normalization, but I'll skip that for now. And then they sort of, for one transformer block, you then go after the multi-head attention, you put things through a feed-forward layer, which also has a residual connection. You sum the output of those, and you then again do another layer normalization. So this is their basic transformer block that they're going to use everywhere. And to make their complete architectures, they're then going to sort of start stacking these transformer blocks to produce a very deep network. And in some sense, what has been found is that transformers perform very well, but there's no free lunch. You kind of can't, you're now no longer getting recurrent information actually being carried along a sequence. You've got a word at some position which can be casting attention on other words. So if you'd like to have information carried along in a chain, you've sort of first of all got to walk the first step of the chain, and then you need to have another layer vertically which can walk the next step of the chain, and then you need to have another layer vertically that walks the next step of the chain. So you're getting rid of the recurrence along the sequence, but you're substituting some depth to allow things to walk along multiple hops. But nevertheless, that's highly advantageous in GPU architectures because it allows you to use parallelization to calculate everything at each depth at the same time. Maybe I'll go light on explaining this as well. So they use byte pair encodings, but if you do nothing else, you just have words fed in as word vectors, and you have no idea whether you're at the beginning of the sentence or at the end of the sentence. So they have a method of doing positional encoding, which gives you some idea as to what position your word has in the sentence. Okay. So that's sort of the encoder system. So from the words, they have an initial word embedding, you add in their positional encoding, you go into one of these transformer blocks, and you then repeat it n times. So you'll have a stack of these transformer blocks, so you're multiple times doing multi-head attention to other parts of the sentence, calculating values, feeding forward a value, putting it through a fully connected layer, and then you just sort of repeat, do attention to different places in the sentence, get all your information, put it through a fully connected layer, and go up, proceeding up deeply. And that sounds a little mysterious, but it turns out to work just great. And the way to think about it, I think, is that at each stage, You can look with your multi-headed attention at various other places in the sentence, accumulate information, push it up to the next layer. And if you do that sort of half a dozen times, you can be starting to progressively push information along the sequence in either direction to calculate values that are of interest. And the interesting thing is that these models turn out to work really well at sort of learning to attend of interesting things in linguistic structure. So these are just sort of suggestive diagrams, but this is looking at layer 5 of a transformer stack and seeing what words are being attended to by different attention heads. So these different colors correspond to different attention heads. And so the sentence is, it is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. And so what we see is sort of most of the attention heads looking from making to making more difficult, and that seems to be useful. One of the attention heads seems to be looking at the word itself. Might be okay. Then the other ones are sort of looking a bit at laws and at 2009. So it's sort of picking out the arguments and modifiers of making in a syntax kind of like way. Interestingly, for pronouns, attention heads appear to learn to be able to look back to reference. So the law will never be perfect, but its application should be just. That one attention head for its is looking at what its is modifying the application, but another attention head for its is looking strongly at what its refers back to as the law. So that seems kind of cool. Yeah. Okay, and so then for the rest of their model, there's then some more complexity for how to use the transformers decoder to give you a full neural machine translation system. But I think maybe I will skip that and go on and say a bit about BERT in my remaining minutes. Okay, so the latest and greatest contextual word representations to help you for all your tasks have been these BERT vectors, where BERT is bidirectional encoder representations from transformers. And so essentially, it's using the encoder from a transformer network, i.e. this deep multi-headed attention stack, to calculate a representation of a sentence and saying that's a great all-purpose representation of a sentence that you can use for tasks, be it named entity recognition or squad question answering. And so there's actually an interesting new idea that these people had, and that their idea was, well, standard language models are unidirectional. And that's useful because it gives you a probability distribution, a language model. But it's bad because you'd like to be able to do prediction from both sides to understand word meaning and context. There's a second choice, which is you can kind of do bidirectional models when you incorporate information in both ways. But that sort of has problems as well, because then you get crosstalk. And so if you run a BioSTM and then you merge the representations by concatenation and then feed them into the next layer, when you're running the next layer, the forward LSTM will have already gotten information about the future from the first layer. So it sort of ends up with words that are already seeing the future in themselves. So you have this sort of complex non-generative model. So somehow they wanted to do things a bit differently so they can have bidirectional context without words being able to see themselves. And the idea that they came up with is, well, we're going to train things with a transformer encoder, but what we're going to do is mask out some of the words in the sentence, like maybe we'll mask here store and gallon. And then so our language modeling-like objective will no longer be a true language model that's sort of generating a probability deliver sentence, which is standardly done by working from left to right, but it'll instead be a Mad Lib style fill in the blank objective. So you'll see this context, which will be literally the man went to the mast to buy a mask of milk, and what your training objective is to say, try and predict what this word is, which you can do with a cross entropy loss to the extent that you don't guess store, and then it will be try and guess what this word is, and you want to guess gallon. So you're training a model to fill in these blanks. And the rate at which they blank words is essentially 1 word in 7, and they discuss how this is a trade-off, because if you blank too few words, it gets very expensive to train, and if you blank many words, well, you've blanked out most of the context of a word, and that means it's not very useful for training, and they found around sort of 1 in 7 seemed to work pretty well for them. But what they want to argue is that for the OpenAI's GPT, which is also a transformer model, it's a sort of a classic language model working from left to right, and so you only get left context. For the BERT language model, the ELMo language model that's shown up at the top, well, they're running a left to right language model, and they're running a right to left language model. So in some sense, they have context from both sides, but these two language models are trained completely independently, and then you're just sort of concatenating their representations together. So there's no sense in which you're actually kind of having a model that's jointly using context from both sides at the time that the pre-trained contextual word representations are built. So their hope is using, inside a transformer model, this trick of blanking out words and predicting it using the entire context will allow them to use two-sided context and be much more effective. And that's what they seem to show. There's one other complication, and I mean, I'll show later. This last complication is a bit useful, but it's sort of not really essential to their main idea, was that they thought one of the goals in their head was clearly to be able to have this be useful for things like question answering tasks or natural language inference tasks, and their relationships between two sentences. So their idea was, well, one good objective is this fill in the blank word objective, which is sort of like a language modeling objective, but they thought it'd be useful to have a second objective where you're predicting relationships between sentences. So they secondly have a loss function, which is let's have two sentences where the sentences might be two successive sentences in a text or a sentence followed by a random sentence from somewhere else, and we want to train the system to predict when you're seeing a correct next sentence versus a random sentence. And so you're also training a loss based on this next sentence prediction task. And so it'll be something like the man went to the store, he bought a gallon of milk. You're meant to predict true is next sentence. The man went to the store, penguins are flightless. You're meant to say false, this isn't a next sentence. And so they're simultaneously also training with this representation. So what they end up looks like this. So they have, for the input, they'll have a pair of sentences. My dog is cute. Separator, he likes playing. The words are represented as word pieces like we talked about last week. So there's a token embedding for each word piece. Then there's a positional embedding for each word piece, which is going to be summed with the token embedding. And then finally, there's a segment embedding for each word piece, which is simply whether it comes from the first sentence or the second sentence before or after the separator. So you're summing those three things together to get the token representations, and then you're going to use those in a transformer model where you'll have losses to the extent that you can't predict the masked word, words, and then your binary prediction function as to whether it's a correct next sentence or not, which is the training architecture. Okay, so it's a transformer as before. It's trained on Wikipedia plus the book corpus. And they built two models. The base BERT model was a 12-layer transformer. And so this corresponded to what the previous transformer paper had used, right? Those 2-layer transformer blocks repeated 6 times gave you 12 layers with 768 hidden dimension hidden states and 12 heads for the multi-head attention. And then they went bigger and trained BERT large, which is sort of double the number of layers, bigger hidden states, even more attention heads, and training these on pods of TPUs. So first of all, you're training on this basis for masked words and next sentence or not. So then what they wanted to say was this pre-trained model evaluated on these losses of masked language model and next sentence prediction. We could then take this model, freeze most of its no, sorry, that's wrong. We could take this model pre-trained, and it would be incredibly useful for various different tasks. We could use it for named entity recognition, question answering, natural language inference, etc. And the way we're going to do it is kind of doing the same thing as the ULMFiT model did. We're not just going to say, here's a contextual word representation like ELMo did. Instead, what we're going to say is, just keep on using this transformer network that we trained as a sort of language model, but fine-tune it for a particular task. So you're now going to run this transformer, calculating representations for a particular task. And what we're going to change is we're going to remove the very top level prediction, the bits that predict the masked language model and next sentence prediction. And we're going to substitute on it, on top, a final prediction layer that's appropriate for the task. So if our task is squad question answering, our final prediction layer will be predicting start of span and end of span, kind of like when we saw Dr. QA a couple of weeks ago. If what we're doing is the NER task, our final prediction layer will be predicting the named entity recognition class of each token, just like a standard NER system. Okay, and so they built this system and tested it on a whole bunch of data sets. One of the main things they tested on was this GLUE data set, which has a whole bunch of tasks. A lot of the tasks there are natural language inference tasks. And I've kept saying that phrase all this lecture, but I haven't really defined it. So for natural language inference, you're given 2 sentences, like, hills and mountains are especially sanctified in Jainism, and then you're given a hypothesis, Jainism hates nature, and what you're meant to say is whether the hypothesis follows from the premise, contradicts the premise, or has no relation to the premise. So it's a 3-way classification, and so here it contradicts the premise. There are various other tasks, such as this linguistic acceptability task. But if we look at these GLUE tasks, these are showing the pre-OpenAI state-of-the-art, how well ELMo works, how well OpenAI's GPT works, and then how well the small and large BERT models work. And effectively, what you're finding is that the OpenAI GPT was, pretty good. It showed actually good advances on most of these tasks. For many, but not all of them, it broke the previous state of the art, showing the power of these contextual language models. But the bidirectional form of BERT's prediction just seemed much better again. So going from this line to this line, you're getting, depending on the task, about 2% better performance. And so the BERT people actually did their experiments carefully, so these models are pretty comparable in terms of size, but the bidirectional context seems to really help. And then what they found was, well, by going to just a bigger model again, you could get another big lift in performance. And so you're getting for many of the tasks about another 2% lift in performance going to the bigger model. So this really produced super strong results. And in general, people have found that BERT continues to give super strong results. So if I return back to my Connell NER task, we had ELMo giving you 92.2, and you sort of continue to get gains. The BERT base gets you to 92.4, and BERT large takes you to 92.8. Though in truth in description, there is now a system that beats BERT large on NER, which is actually a character level transformer language model from Flair. But, you know, this continued over to a lot of other things. So on Squad 1.1, BERT immediately just outperformed everything else that people have been working on for Squad for ages. In particular, what was especially dramatic was a single BERT model beat everything else that had been done previously on Squad version 1.1, even though they could also show that ensemble of BERT models could give further good performance gains. And as I mentioned before, essentially if you look at the Squad 2.0 leaderboard, all of the top ranked systems are using BERT one place or another. And so that sort of led into this sort of new world order that, okay, it seems like the state of NLP now is to, if you want to have the best performance, you want to be using these deep pre-trained transformer stacks to get the best performance. And so this is sort of making NLP more like vision, because really vision for 5 years has had these deep pre-trained neural network stacks like ResNets, where for most vision tasks, what you do is you take a pre-trained ResNet and then you fine-tune a layer at the top to do some classification task you're interested in. And this is sort of now starting to be what's happening in NLP as well, that you can do the same thing by downloading your pre-trained BERT and fine-tuning it to do some particular performance task. Okay, that's it for today, and more on transformers on Thursday.